Your engine computer relies on a network of microscopic sensors to balance air, fuel, and spark thousands of times per minute. If just one mass air flow or speed sensor feeds corrupted data to the ECU, your fuel economy drops 30%, your transmission slams into gear, and your catalytic converter melts. Here is what every single key sensor actually does, and how to spot them failing before you get stranded. To understand how a modern engine functions, you have to realize that mechanical components like pistons, valves, and crankshafts are completely blind. They rely entirely on an electronic nervous system overseen by the Engine Control Module, or ECU. The ECU's primary task is maintaining a precise stoichiometric air-fuel ratio, exactly 14.7 pounds of air for every single pound of fuel burned. To achieve this continuous balance, the computer must know the exact volume and density of air entering the intake manifold. First is the mass airflow sensor, or MAF sensor. Located directly in the intake pipe between the air filter box and the throttle body, the MAF uses a delicate, electrically heated platinum wire exposed to the incoming airstream. As air flows past the hot wire, it strips away heat. The sensor's internal circuit continuously increases electrical current to keep that wire at a fixed temperature. The engine computer measures this current surge to calculate the precise mass of incoming air in real time. When a MAF sensor fails, usually caused by fine road dust or oil residue from cleanable air filters coating the platinum wire, it becomes insulated. It underreports the actual volume of incoming air. Thinking less air is entering, the computer underinjects fuel, forcing the engine to run dangerously lean. Common symptoms include severe hesitation during acceleration, engine surging, rough idling, and system lean diagnostic codes like P0171. Alternatively, many modern turbocharged or speed-density engines rely on a manifold absolute pressure sensor, or MAP sensor. Instead of measuring air mass directly with a hot wire, the MAP sensor mounts directly onto the intake manifold plenum to measure internal vacuum and positive boost pressure. Inside, a silicon piezoresistive diaphragm flexes under pressure changes, sending a corresponding voltage signal directly to the ECU. When a MAP sensor gets clogged with PCV oil vapor or experiences vacuum hose leaks, the ECU loses track of engine load. The vehicle enters a restrictive backup mode, resulting in heavy exhaust soot, sudden engine stalling under load, and awful fuel economy. Once air passes the intake filter and airflow sensors, it meets the primary gatekeeper of engine speed, the throttle plate. To adjust fuel delivery, ignition advance, and automatic transmission shift points, the computer must instantly know how far you are pressing the accelerator pedal. This is managed by the throttle position sensor, or TPS. In older vehicles, the TPS was a simple mechanical potentiometer. In modern drive-by-wire vehicles, dual Hall-effect magnetic position sensors track both the gas pedal assembly under your foot and the electronically driven throttle plate inside the engine bay. When a TPS wears out, its internal electronic contact tracks degrade or its magnetic sensors experience voltage drift, creating digital dead spots along the pedal travel. If you step on the gas and hit one of these dead spots, the computer loses track of pedal position for a split second. The engine will hesitate violently, buck, or instantly trip a safety threshold, locking the car into a reduced power limp mode, where engine speed is capped for safety. While airflow sensors measure incoming air mass, the computer cannot fire a spark plug or pulse a fuel injector without knowing the exact physical position of the moving internal engine parts. This critical timing coordination requires two rotational sensors, the crankshaft position sensor and the camshaft position sensor. The crankshaft position sensor, or CKP, monitors a notched reluctor wheel attached directly to the spinning crankshaft or flywheel. It sends a high-speed digital pulse stream that tells the computer three critical facts: engine RPM, exact crankshaft rotational angle, and individual cylinder misfire events by tracking tiny microsecond variations in crankshaft acceleration. If the CKP sensor fails completely, the result is absolute. The engine will crank indefinitely but will never start. Without a reliable crankshaft signal, the computer disables both fuel injection and ignition spark to prevent timed combustion from destroying internal hardware. A failing CKP often exhibits heat-induced electrical failure. The engine starts and drives fine when cold, but cuts off completely like someone pulled the key once the engine reaches operating temperature. Working in direct synchronization with the crankshaft sensor is the camshaft position sensor, or CMP. While the crankshaft spins twice per cycle, the camshaft spins only once. The CMP tracks the rotation of the intake and exhaust valves to tell the computer which specific cylinder is on its intake stroke versus its exhaust stroke. This precise data enables sequential fuel injection and controls high-speed variable valve timing, or VVT actuators. When a camshaft position sensor degrades, the engine loses timing phase synchronization. This causes extended starter cranking before the engine catches, rough idling, noisy timing chain operation, and a dramatic loss of top-end power as the VVT system locks out for protection. Liquid and air temperatures dictate basic internal mechanical clearances, oil flow properties, and overall thermodynamic efficiency. To manage cold starts and thermal protection, the computer relies on a dedicated suite of temperature thermistors. The engine coolant temperature sensor, or ECT, measures internal engine coolant heat near the thermostat housing. During a cold start, the computer reads high resistance from the cold ECT and commands a rich air-fuel mixture alongside elevated idle speeds to warm up the catalytic converter. If the ECT fails cold, the computer assumes the engine is perpetually frozen. It floods the cylinders with continuous excess fuel, leading to black tailpipe smoke, fouled spark plugs, fuel-diluted engine oil, and terrible fuel consumption. If it fails hot, the computer starves a cold engine of necessary fuel, making it nearly impossible to start, while also failing to trigger the electric radiator fans, leading to swift engine overheating and blown head gaskets. Working alongside the coolant sensor is the intake air temperature sensor, or IAT. The IAT measures the temperature of incoming atmospheric air. Because cold air is denser than hot air, the ECU uses IAT data to fine-tune fuel injection quantities, delivering crisp throttle response whether you are driving through sub-zero winter air or blazing desert heat. Modern performance, turbocharged, and heavy-duty utility engines also rely on the engine oil temperature sensor, or EOT. Because motor oil heats up significantly slower than engine coolant, the EOT sensor informs the ECU when the oil has reached its ideal operating temperature and viscosity. Until the oil is properly warmed, the computer restricts high RPM rev limits and disables variable valve timing mechanisms to prevent metal-on-metal wear on delicate camshaft lobes and engine bearings. A failing EOT sensor can leave an engine feeling lethargic, trapping it in a permanent protection mode. Beyond internal engine RPM, the vehicle's central computer network must track how fast the vehicle is physically traveling over the road. This critical job belongs to the vehicle speed sensor, or VSS. Mounted on the transmission output shaft, transfer case, or integrated into the wheel hub assembly, the VSS measures the physical rotational speed of your driveshaft or wheels. This pulse data is shared across the ECU, transmission control unit, and braking modules. When a VSS fails, the symptoms extend far beyond the dashboard. While your speedometer needle might drop to zero or bounce erratically while driving, the real danger happens inside the drivetrain. The automatic transmission relies on speed data to determine gear selection and hydraulic pressure. Without a clean VSS signal, the transmission will shift harshly, slip between gears, or lock itself into a single limp mode safety gear. Furthermore, cruise control will immediately shut off, and your anti-lock braking and traction control systems will illuminate fault lights on your dash. After combustion occurs inside the cylinders, spent exhaust gases exit through the exhaust manifold, where the computer performs its final feedback loop using oxygen sensors, or O2 sensors. The primary upstream O2 sensor, often a wideband air-fuel ratio sensor, sits directly before the catalytic converter. It measures the amount of unburned oxygen remaining in the raw exhaust stream, generating a dynamic voltage signal that tells the computer if the combustion mixture was too rich or too lean. The ECU monitors this reading thousands of times per minute to adjust injector pulse widths in real time, a process known as short-term fuel trim. If the upstream sensor becomes sluggish due to oil burning or carbon contamination, it sends delayed readings. The engine fluctuates wildly between rich and lean states, wasting gas, causing engine surging, and sending unburned fuel into the exhaust pipe where it ignites and physically melts the ceramic core of your catalytic converter. The secondary downstream O2 sensor sits after the catalytic converter. Its sole duty is monitoring the chemical efficiency of the converter itself. If its signal begins to fluctuate and mirror the upstream sensor, the ECU knows the catalytic converter has degraded, instantly triggering the infamous P0420 fault code. The final line of defense shielding your engine block from complete physical destruction is the knock sensor. Bolted directly into the metal structure of the engine block, the knock sensor is essentially a specialized piezoelectric microphone tuned specifically to the high-frequency metallic vibrations of engine knock, or detonation. Knock occurs when unburned fuel ignites prematurely due to excessive cylinder heat, poor fuel quality, or advanced timing, sending violent shockwaves that can shatter pistons and snap connecting rods. When the knock sensor detects these specific pre-ignition frequency spikes, it sends an immediate signal to the ECU. Within milliseconds, the computer retards ignition timing, stopping the destructive shockwave before internal hardware gives way. If a knock sensor fails due to internal corrosion or damaged wiring, the computer can no longer detect pre-ignition. To protect the engine from destroying itself, the ECU permanently retards ignition timing and limits turbocharger boost pressure. The vehicle will instantly feel sluggish, suffer a major loss in horsepower, and illuminate a persistent check engine light. Every sensor inside your engine bay serves as a vital link in a high-speed electronic feedback loop. A single $50 sensor failure can easily mimic major mechanical damage, leading drivers to waste thousands of dollars replacing perfectly good fuel pumps, catalytic converters, or complete transmissions. By understanding how MAF, crankshaft, speed, and oxygen sensors communicate with your vehicle's brain, you can accurately diagnose fault codes and keep your car running smoothly for miles to come. If you found this technical breakdown valuable, hit the like button, subscribe to the channel, and drop a comment below with the current fault codes your car is throwing. Keep your sensors clean and keep your intake breathing freely.